if our symbol table is really going to be dynamic, we need to be able to delete key value pairs from the table. As we'll see, all symbol table implementations lead to complications when we try to do this operation. Binary search trees is our first example. So we need to fill in this one table. What's the cost of deletion in a binary search tree? How are we going to really do that? Well, let's take a look at a very lazy approach, which we set up for in our basic conventions for symbol tables. What we can do to remove a node with a given key is just mark it with a tombstone. Say, well, we'll leave the key in the tree to guide searches, but we won't count it as being in the symbol table. And actually, you can make some progress with this kind of method, leaving tombstones throughout the tree, and make sure that you keep, as long as there aren't too many deletions, you can keep the search cost and deletion and insert cost to be logarithmic. But it definitely becomes inconvenient to manage large numbers of tombstones in highly dynamic situations with large numbers of keys and values. Eventually, you're going to get an overload of memory and you're going to have to rebuild the thing or clean out the tombstones in some way. So we need to look for a better way. This is a general method that people often use in all different types of implementations, but in modern systems it's rather unsatisfactory. Well, let's look at a simpler problem. What about deleting the minimum? Actually, that's maybe not too difficult. To delete the minimum in a binary search tree, again, we just go to the left until we get a null left link. And then what we can do is just return that node's right link. Then that old node, nobody's pointing to it, so it's available for garbage collection. And then we use our usual trick of returning the link that we went down to update the other links after the recursive calls. And also, we have to update the counts. Something happened down below, and we use that code to update the counts in a consistent way. So this code implements delete min. Not too bad at all. If x.left equals null, return x right. Otherwise, x left equals delete min x left. And then when you're done with that, you fix the count. Maybe a node got deleted down there, but always the invariant is that the count at a node is 1 plus the size of the left and right, and then return x and fix the links and the counts on the way up. That's a fine implementation for delete min, and it also works for delete max. And that's the basis for a general method for deleting nodes from BSTs known as Hibbard deletion. That's the second case. The first case for Hibbard deletion is what we want to do to delete a node with key k is we search for the node that contains the key. And the easiest case is that node has no children. So to delete a node that has no children, just return null. And then go back up to update the counts as usual. That's the easy case. The next most difficult case is like the delete min case. We find a node T that contains our key, so like deleting R in this tree. It only has one child. Just go ahead and return the link to that child, and that updates the link and everything works fine. Then the node that was deleted is available for garbage collection because nobody's pointing to it. And again, update all the counts after the recursive calls. So 0 children, no problem. 1 child, no problem. The problem is what happens when there's 2 children. So say we want to delete node E in this tree. We have only one link. We can get rid of the node, but we have only one link pointing to it, but we have 2 links pointing down from it. So what are we going to do with those 2 links? Well, the Hibbard deletion mechanism, which is pretty old, 50 years ago it was proposed, says go ahead and find the next smallest node in the right subtree of that tree. So in this case, that's H. And what's that node? Well, it's the minimum in T's right subtree. And we know how to delete the minimum, so we just find that minimum node, and in this case it's H, and we put that node in T's spot and then delete the minimum. So find the H, that's the minimum, hang on to it, and then delete the minimum in T's subtree, and then so we take the E, replace it with the H, and delete the H, and then everything's fine. It's still a BST. So we're finding a node that has only one link, and deleting that node, and then replacing the node that we need to delete with that one. That's Hibbard deletion. It's a little bit asymmetric. Why are we using the successor and not the predecessor? No real reason. And it's not really satisfactory because of that, and we'll come back to this, but it works. So this is the code for Hibbard deletion. So we search for the key. If it's got no right child, we're fine. We just return x.left, and that handles both cases 0 and 1. If it does have a right child, then we do this find the minimum on the right, delete min on the right, and then fix the links, and then update our count that covers all cases. So actually not that much code. It's complicated, but not particularly more complicated than other code we've seen, like rank and floor and ceiling, and that implements Hibbard deletion. So now we have a fully dynamic symbol table where we can insert and delete. The number of nodes that we have in the tree is always proportional to the number of key value pairs in the symbol table. And the problem is, and this was quite a surprise when it was first discovered, actually many years after Hibbard proposed the algorithm, is this lack of symmetry tends to lead to difficulties. And here we're just inserting, deleting, alternating, insert and delete a random key. So that maybe well models a situation, a practical situation. And as you watch it go for a while, you can see that this thing about going to the right and taking the successor all the time, the tree's becoming much less balanced than it was. And this seems to be a problem. We can't be supposedly having a dynamic situation that is going to allow support of lots of different inserts and deletes, and in the end wind up with a less balanced tree. What's worse, so how are we going to fix it? So in the end, researchers showed that after sufficiently long sequence of random inserts and deletes, the height of the tree becomes square root of n, not log n. Square root of n is hugely bigger than log n. It might make the difference between acceptable and unacceptable performance in real applications. And what's worse, if you try to fix it by, say, randomly choosing between the left and the right, that doesn't work. It still becomes square root of n. And it's a very long-standing open problem to find a natural, simple, efficient delete for binary search trees. That's another one like merging in place that you'd think there ought to be an easy way to do it, but in 50 years, no one's really discovered one. We're going to look at something pretty close in the next lecture, but here's the situation that we're left with. We have a binary search tree algorithm which is fine in that it gives us log n performance for search and insert in a situation where we can think that these things are happening randomly. But we're kind of stuck if we allow delete. In fact, everything degenerates to square root of n. And we also have the problem with the worst case. If the keys happen to have some order in them, our trees are not going to be balanced at all. And that's going to make the difference between acceptable and not acceptable performance. What we're going to look at next time, called a red-black binary search tree, will guarantee logarithmic performance for all operations. That's extremely significant and much better than binary search trees. But the delete operation for binary search trees shows us the kind of complexity that we can encounter with working with these kinds of data structures.